Sir?
Thank you. I was sort of challenged to try to do something useful with the concept of the deep orbit electrons. And one of the things that had come up was, of course, the nuclear remediation. And some of the strange results coming out of the cold fusion community is the low radiation. And so we're trying to explain what's actually happening. In terms of background, the atomic s orbital electrons pass through the nuclear region of an atom, but they pass through at a relativistic velocity, and it's a very, very small portion of their orbit. The Coulomb potential in the nuclear region makes these electrons relativistic. And the calculations that Jean-Luc Pellet has been making says that they are highly relativistic. I think that there's actually two paths, one with the 100 MeV kinetic energy and one with maybe just the 1 to 2 MeV. So this paper is actually based on earlier results, which I considered to be the 1 to 2 MeV range, and it can be carried over into the 100 MeV range. But the point is that we actually have the quantum mechanical, relativistic quantum mechanical equations which predict the deep orbits, and they would predict them for either range because the equation only comes up with the binding energy. And when you have highly relativistic electrons, the virial theorem says that the binding energy, that the potential energy and the kinetic energy approach the same point in a highly relativistic environment. In a non-relativistic environment with a central potential, Coulomb potential, your kinetic energy is 1/2 of the potential energy. But as you get to the relativistic regime, they come closer and closer together, so you can maintain this fixed binding energy and have a whole range of possible energies. The question is, do you have resonances there that will give you a stable orbit? Classical physics says you can have electrons in this region, but they're not stable there. In prior papers, we explored the nature of the deep orbits and the relativistic equations. One of the things that is an obvious consequence of the deep orbit is that you're creating femto-atoms, femto-hydrogen, femto-deuterium, and actually I think we're creating a femto-helium, which is, I would consider that just to be a neutral alpha particle. And the femto-hydrogen would be just a fat neutron. So it's a neutral particle that penetrates the electron cloud around an atom, and it penetrates into the nucleus without any impedance there. Now, one of the things which is important in this whole process, which is, I consider the major thing that started things, is the process of transferring nuclear energy into the lattice. The binding energy of these deep orbit electrons is close to 1/2 MeV. And this means that you can excite this electron in the nuclear field from an excited atom and still maintain its highly bound. You can go ahead and pump 200 kilovolts into it, which can then re-radiate into the environment. And we've talked about these things in the, well, I guess I better use the right one. So we have a lot of papers that have been written on these things, and we have also some display on of these slides in the poster session. So penetrating radiation-free transmutation is predicted by the deep orbit model. The question is, why? What's actually going on that allows this? In the normal transmutation from neutron activation, It's a two-body interaction. It has a unique product and limited decay paths. So you have clean gamma decays and or beta and other things which are highly predicted and very, very well known. In the femto-body transmutation, as a multi-body interaction, it has many transmutation and many decay paths. And so there is a sharing of the energy through the different paths and a competition between the energies. But just like in ion implantation, you go ahead and put an ion into a material, it splits up when it hits that material. In this case, in many cases, even though you have a high binding energy, by the time you hit a nucleus, the energy available may be so large that it splits up. And now you have, within this nucleus, you have the product, which is typically going to be a proton or a deuteron and a deep orbit electron. And this gives you multiple paths, gives you multiple interactions within the nucleus. And so you have decay paths which are not unique. You don't have the unique lines, and now you're ending up with a spectrum or a spread of energies. And I'll tell you another reason later on what that is going on. And this is what has been observed in cold fusion results. So within those results, we have the strong nuclear forces going on, we have the weak nuclear forces, and we have electromagnetic forces. And with the relativistic electron, it looks like the electromagnetic forces may be as strong as these others. And one of the things that fits is that the presence of this relativistic electron with factors in their field strength and what's going on, because it's relativistic, these may be 100 times or 200 times stronger. So it's going to really disturb what's going on in the nucleus. So you're not going to go ahead and get the characteristic gamma lines. Other things are going to be happening. One of the keys here is decay is a statistical process. And when you destroy the stability of a situation, you go ahead and change the statistics. And this is what gives you line broadening in one respect. And that fits with the standard model, so that works okay. The different components of the fat neutron, the deep orbit electron, is that you have relativistic electrons in the nuclear region. And the problem, my view of the problem of the weak interaction, and I would like to go ahead and discuss this with other people who know what's going on better. The weak interaction to me is considered weak because it's improbable. And it's improbable because the interaction is a transient with a fast electron coming in, or a three-body problem where you have to have an electron and an antineutrino coming in and combining at the same time. However, when you're talking about a deep orbit electron, it's there all of the time. Not only that, it's resonant with the nucleon frequencies. So you're actually having a close resonant process which makes the weak interaction very fast. Is it a weak interaction in those conditions, or does it become a strong interaction? But with the process and these interactions, you're going to get the output of the neutrinos and photons, but they're not going to be the characteristic lines of the normal process, the normal neutron activation. You have direct energy transfer, and I'll show you in a moment why that is the case, but you don't have to have photon interactions. And you have internal conversion processes and things which don't need, or they don't actually call about photons, but QED, of course, says that any magnetic field, electric field is a photon. Okay, so I've got a Cadillac because I have a steering wheel. I don't know. But internal conversion becomes very important. And the reason for that is that we don't really have a lot of evidence yet of the deep orbital electrons. And internal conversion peaks at low energies. So if you have an energetic process, the energy transfer is such that the deep orbital electron transmits energy from the nucleus into the lattice, and it loses energy in the process. And when you get to low energies, then it itself can get kicked out. The other actions are that you can have a neutron created by the proton and electron. You can actually have the weak interaction right there. So now you have a neutron. It can also kick out neutrons. So these pathways are neutron absorption or neutron ejection. And that's going to have to do with the preference of the energetics of the nucleus. The same thing with protons. If you have a fat neutron coming in, you've got that proton. It can be accepted into the more stable, or make the more stable nucleus. And the process can also kick out a proton. So you really have multiple pathways, and the multiple pathways destroy all of the observations that we know so well from the neutron activation. Now, what's going on? Why am I talking about this fat neutron or this relativistic electron having an effect on the lattice atoms and actually lowering radioactivity? The thing that comes out of Feynman's lectures is this equation, and it has two terms in it. The one we're most familiar with is just the relativistic correction, but it also has another term which has to do with acceleration. This first term is velocity dependent, this is acceleration dependent, and you can look at the beta prime, beta is v over c, so this is an acceleration term. In atomic physics, non-relativistic physics, this is the primary one. So the relativistic deep orbit electrons have the Fermi size deep orbits near c velocities and frequencies which are comparable or near those of the nuclear frequencies. I'm not going to go through these equations, but what I'm pointing out is that you can take these two terms and you can go ahead and do ratios and take out a lot of these things, and you can come up with numbers that can give you some information. Number two is, for instance, just taking the Coulomb term at the atomic level and compare it to the radiation term, and you can see that it is much larger. And being much larger, you can just ignore the acceleration term, and that's the range we normally think about. But in number three, where you're looking at the Coulomb potential of the deep orbital electron, this is the DDL, is the deep Dirac level, and compare that with the radiation field, now they're closer to being comparable. If you go ahead and look at the effect of the proton on number four, the Coulomb field of the proton, and now looking at the far field, if we look at the electron far field and compare the two, you can ignore the proton. It's just only going to be the radiation field, and that's going to be a high frequency field. So then on number five, you have the deep orbit far field and the proton near field. Now the reason I do this is this goes ahead and tells you the transfer energy rates between the nucleus and the deep orbit electron and the deep orbit electron out to the far field, out to the lattice. And then if you go ahead and compare these results, say in number six, the far field is very much stronger than any effect from the nucleus itself. So the key here is that the electromagnetic fields from the deep orbit electron are much stronger than that from the Coulomb potential. And what we see is that the Coulomb potential, the field is 1 over r squared, whereas the acceleration potential, electromagnetic potential, is 1 over r. This means this is a long-range field relative to this. So the further you go, the less effect you have from the Coulomb potential, and the most effect you have from the acceleration. And of course, that electron, very tightly bound, has a very strong acceleration around the nucleus. So the keys of the nuclear coupling with the deep orbit electron is that the comparable nucleon frequencies, the coupling is very strong. The Coulomb field is multiplied relativistically by a factor of 200. This is sort of what I was showing in the earlier presentation, Jean-Luc's presentation, showing a gamma of 200 is quite likely. Even if it's not that high, even if I'm right and there also is a low energy, an MeV electron, it's still relativistic, and you still have very, very strong coupling because it's so close. Now, one of the things that we have, that if the frequencies of the deep orbit electron are comparable to nuclear frequencies, then we have the possibility of induced radiation, spontaneous emission induced by the field, the strong field, which is not just the near field, but it reaches out to all the neighboring nuclei. This actually gives you the capability of creating forces. We talk about, whether it's valid or not, the model of the Coulomb potential being a photon exchange. Well, here we're in a situation where we're creating strong forces. They're not photons, but there are strong potentials, fluctuating potentials. So we can actually go ahead and start changing energy levels, and in the process of changing energy levels, you have the ability to do work. So as a consequence, the nucleus with the high velocity electron around it actually is drawn as a unit to any nucleus nearby, but it's particularly drawn to unstable nuclei where you can go ahead and make major changes in energy. So how does this lead us to selective transmutation? We've stated that the deep orbital electrons are attracted to lattice protons, but this, because they're so tightly attached to the nucleus, they're dragging the whole femto-atom into the other lattice nuclei. And they're most attracted to the excited nuclei because now you have energy transfer on a major level. You can go ahead and lower the energy system by a great deal. But this also means the possibility that we're able to go ahead and de-excite these other nuclei without the normal emissions. Therefore, you're not going to see the same transitions. You may not see any characteristic lines at all. And even if you do have characteristic lines, they're going to be highly broadened because of the strong field presence. So then the question comes up is there a physical process that can allow the femtoatom to sense the presence of a excited or unstable nucleus? And this goes back to something that when I first met Peter, he was talking about a process that actually pertains. And so I'm sort of excited to sort of close the loop, and he still is working on things that fit this area. But to test this model, if this model is correct, we are able to dope an active cold fusion experiment and see the specific consequences of that in terms of the transmutation products. So this is something that once we have active systems that are reliable, and this is something that Mitchell and I were talking about something else, but this works out in his system, we could go ahead and dope the material with specific isotopes and see the consequences. And I think this would pretty much verify some of the things going on. So a nucleus is actually doing work when it draws another nucleus to it. If you have an electron there neutralizing it and you're being drawn by the field from the electron, there's work being done by the nucleus because it's doing work in maintaining the presence of the electron. You have very strong electromagnetic fields. That deep orbit electron is actually altering the charge spacing. It's polarizing the nucleus. It's doing things that allow the nucleus to change its mass. This is the basis of earlier papers talking about why we don't have the normal decay in the DD interaction. This is the answer to that. Now, one of the things that I object to in a lot of the concepts of the quantum mechanics is that they use a time-independent model, and therefore the transitions never show up. Well, these transitions are not instantaneous, they're a process. And you can actually predict what's happening during that process, and that tells you a lot about what to expect. So what do we have as the basis for nuclear waste remediation? We have the neutral femto-atoms. We have the near-field attraction of the deep orbit electron with the nucleus, and because it has a larger radius than the nucleons and it's relativistic, the ability to transfer energy out is much greater than that could be done by a nucleon. So therefore, you have the ability to transfer energy, near field forces from the nucleus to the electron to the lattice. And it's sort of the same thing that if you have two atoms and one's excited, you transfer the energy through a photon. It's sort of an impedance matching process. It's not really, but it's the idea. Here's a situation where the deep orbit electron is the matching process between the nucleus and the lattice. The question also comes up then, is the weak interaction really weak? And if the deep orbit electron is valid, if that model is valid, then it should have a major impact on the concept of weak interactions. Number 5 here is we have multiple paths for the decay. It induces things, it creates new things, preferentially in terms of the energetics, and we then have also the concept of direct excitation of the lattice electrons. If you have this very strong field, but very high frequency field generated by the deep orbit electron, on an atomic electron, it simply goes ahead and vibrates the orbit very rapidly, and you don't notice that. But if that electron is vibrated when it's close to its nucleon during its transit for an s orbital electron, all of a sudden that small change during that short period of time can change your energy levels dramatically. So you can transfer energy to the lattice s orbital electrons, knocking it out of that orbit, and then ultimately you have another decay of an electron to that s orbit. So you should get characteristic lines coming out. However, the fields are so strong and the disturbance is so great that you're going to get a lot of spreading. So you're going to see broad lines where you should normally, we would expect to see the characteristic radiation. So this gives us a lot of processes going on that explains much of the data that's been observed in cold fusion. We'd like to see more data that can confirm it directly, and it looks like the possibility of Mitchell's work, there may be a way of doing that because we have the ability to actually look into the insides of a reaction. And if we can look at the anti-Stokes line, we may be able to see some of the characteristic things created by these electrons. But the relativistic deep orbit electron explains a lot of things that we're observing in cold fusion. Thank you.
Thanks very much, Drew. Do you have any comments or questions, please?
Just maybe simple but complicated at the same time. Your model, for some aspect, is not too far from the model of Olofsson and Holmlid about femto-atom. So can you say in a few words which one is the main difference? So can help both.
Okay.
Thank you.
Mills actually predicted deep orbital electrons, but not the same depth. They're sort of a one-over process, so it's a spread of energies below the atomic ground state. The classical physics allows you to go ahead and have the electron going through a sort of a convoluted orbit close to the nucleus, but it's not a stable orbit, at least not unless you get into models, which I haven't gotten into yet. But in the process of looking and saying that, hey, we can get electrons trapped in this region, or close to being trapped in this region, and then I found some of the papers that actually had been given to the cold fusion community as early as 93, 94 publicly, I think. The mathematics, the relativistic mathematics, quantum mechanics, gives you the deep orbit. So here we're taking something which should be standard physics, except it has for 50 years been argued about because it requires, within the mathematical physicist's mind, a Coulomb potential which is singular at r equals 0. Well, we know that no proton has all the energy of the universe in it. That's sort of like having the humorous comment that you can go ahead and have one electron going back and forth in time, so the whole universe has one electron. Well, these singularities are mathematical games. It doesn't work that way. So,
just an interesting comment. The suggestion then is it might be able to determine whether this effect is occurring by, say, doping cesium-137 into a running cell. And if you're getting, let's say, neutron capture, you'll go one way, but this implies that you do something else. And so doing a TOF sims afterwards would be a way of backing it out. What's very interesting is this is almost exactly what Imamura was trying to do, using stable elements, then substitute the hot ones. And the question is whether this is behind that.
yeah. I think there's a number of ways of doing it, and it depends upon having a reliable system. Otherwise, you're spending a lot of time. But by looking at the energetics, and in one of the papers, Bill Collis provided me with the energetics of a lot of reactions, and you can pretty well point which way you're going to go in those reactions. So I'd have to look at the 137 specifically and see what I would predict from that. But for those who are interested, the past couple of days after talking with Mitchell, I'm sort of thinking about what kind of reactions we could actually see and use, and it could be very quickly that we could actually prove that this is actually happening. And if it is happening, once we're confident about that, then we can start looking at ways of making it happen. And that's, of course, the goal of everything here. This is talking with Jed as well. He brings up, make it practical, make it real.
Thank you
Thank
very
you.
much, Drew.